Part 22 of my book Causation and the Universe, a bridge between the 1900s and the 2000s, by me, Roger Michael Klang. Shut up and calculate. If I with military terms would try to explain the macro world and the micro world, I'd say that macro is strategy and micro is tactics. Here we have two different ways in how to think, and you may be good at one, but not good at the other. Yet they are both indispensable, from the small to the big, for the outcome of a war. And there is no clear interface between the two. Strategy is about the bigger goal, and tactics is about the detailed means to reach this bigger goal. An opposite analogy would be if strategy is compared with relativity and tactics is compared with quantum mechanics. But how does this apply to the theory of relativity versus quantum mechanics? Suppose that the right preconditions in the double-slit experiment setup have been met so that we can emit individual photons subsequent through two adjacent double slits. It will then display a wave pattern or interference pattern on a front screen, just like if the light was water passing through both slits and interfering with itself on the other side. If we measure the light prior at the slits, and thereby define or fix the photon, we find that the interference pattern on the front screen collapses and the light waves suddenly appear as a particle, i.e., it traverses just one of the two slits. That is how we know that light cares about being observed or not. And that is also how we know that light is a wave particle. In addition, we have no way of telling exactly where the emitted photon particle is going to end up on the end screen. It can show up at any of a finite number of probability-defined pattern places if you emit many single photons subsequent, but only if you don't measure the light at the slits. Even a single emitted photon will show up at any of a finite number of probability-defined places. Prior, the wave particle was in a probability state. When a photon is emitted, it is emitted as a particle, and when that photon hit the end screen, it is again a particle. But in between, it is a wave. But if you observe it in between at the slit, it is a particle. And it is a particle all the way from the emitter to the slit, since there is an absence of interference pattern on the front screen. And that can only be if the light knows in advance that it is going to be measured at the slit. At the very instant you measure a single photon at the first slit, at the other slit there is no longer any wave particle traversing. Nothing is stopping it from doing so but the wave particle itself. Make a cavity at each slit, and I don't think the result will differ. Thus, light, already from the start, must know that it will get detected at the one slit. That is my understanding. So indeed, it is weird, and our brains will never be able to fully understand or correctly perceive the physics of a wave particle, since our brains are not wired for that. But somehow this unintuitive result, which to us looks like magic, is solid-state physics. We will at some point in time finally have to learn to accept that, I think. But even if we cannot grasp the how, we may still be able to understand the why. It is like a magician that does a trick. We don't know how he does it, but we have clues to how the deception is set up. All double-slit experiments ever rigged are important clues. I may add that even if we measure the emitted light at one of the slits, thereby causing the wave to collapse into a particle, there will be a pattern for subsequently emitted photons at the end screen, only with less fringes than an interference pattern. We only know the particle supposedly is a particle at that instant because it traverses just the one slit we measure at, and because we can localize it. And also, it is not sufficient to merely with your eyes look at the light for the interference pattern to disappear. Something has to interact with the wave particle for the wave to collapse. We need a measuring device for that. The double slit experiment. You never measure P, but you calculate the predicted time of impact on end screen for P. You can additionally do this experiment in a medium, like for instance water or a gas. If you can emit a number of photons at attosecond intervals, you can see whether an interference pattern appears or not when you measure the subsequent photons at the double slit, before the first photons have even hit the end screen. 1. If the end screen doesn't display an interference pattern whatsoever within the given time span, then the whole set of subsequent emitted photons have been particles all the way to the screen, even at the stretch when and where the first photons traveled, prior to the moment you started to measure the follow-up photons at the double slit. Look at the image. 2. But since subsequent emitted photons make a pattern on the end screen, even when measured at the slit, it is more of a proof that the wave particle is both a wave and a particle simultaneously. Conclusion. It is difficult to mentally digest, but 1 and 2 may both be equally correct. We pre-emit a number of photons which together can display an interference pattern if they hadn't been measured at the double slit. But we don't measure them at the double slit at this moment. We initiate the measuring of the subsequent emitted photons at the double slit some femto or attoseconds later. But at this moment, when we start the measuring at the double slit, the first emitted photons have yet to reach the end screen. When we initiate the measuring, we check if the photons which were emitted some attoseconds earlier, when we were not yet measuring at the double slit, if they form an interference pattern on the end screen or not. That is why the photons have to be emitted with super short intervals. Then we would know if light is immediately linked not just to its past, but to its past and its future simultaneously. If the end screen doesn't reveal an interference pattern, then we have proved that light is linked not only to its past, which has already been confirmed in experiments, but also to its future, and hence, in theory, information can be transmitted faster than light speed, even immediately, over vast distances. If light can be established to be immediately linked to not just its past, but to its past and future simultaneously, then the implications are mind-boggling. It would inevitably imply that from the moment light leaves a distant star, and if we eventually detect this light here on Earth, the light would know prior, from the moment it leaped from the star, that it would get detected even though the distance to this star is billions of light years. It in turn would imply that the property we call distance or space has no real meaning for light, and that the information can be transmitted faster than light speed, even immediately, for massless photons, but not as seen by us detectors. But then, how does light know its speed limit? Surely it must have a speed limit, since distance divided with time equals velocity equals d divided with t. Yes, and it is 299,792,458 meters per second in vacuum. But I think the speed limit of light is observed as the speed limit only for us non-particles. Whatever the case, this hypothesis is easily falsifiable. This experiment has the potential to explain how two particles can be in a quantum entangled condition, where the one particle immediately can know the spin of the other particle.